Now, starting from the chi-square test of homogeneity, this is the simplest type of the chi-square test, and it is the test for homogeneous frequencies. So in this test, the assumption is that the frequency distribution is uniform in all classes or categories. So all of the classes or categories that you have, the frequency distribution of your variable is uniform in all of those classes. It should be homogeneous, that there should be no difference, there should be no significant difference in frequency distribution of your variable among different categories or among different classes. So this is the basic assumption of the chi-square test of homogeneity, which is the test for homogeneous frequencies. And we are going to take the example of Dixella insects. So a biologist collects a sample of Dixella pupae from a pond, and these pupae, they are morphologically indistinct. They are morphologically similar to each other, and they emerge out in following numbers: Dixella autumnalis, Dixella aestivalis, Dixella amphibia, and Dixella attica. So these are the 4 species of the Dixella that are present in that community, that are present in that pond, and they emerge out in these numbers: Dixella autumnalis 24, Dixella aestivalis 32 out of the 75 pupae, Dixella amphibia 10 out of 75 pupae, and Dixella attica 9 out of 75 pupae. So this is their frequency distribution. So these species, they are the classes, they are the nominal categories, and these are their frequencies, which are the number of pupae belonging to respective species. So this is the kind of distribution that you get. So unless and until you have some previous observation or previous finding that what is the species composition in that community or what is their relative distribution, so unless and until you have that, you have to assume that these are homogeneously distributed, that their distribution should be homogeneous. So apparently we can see that these are not homogeneous. So out of 75, Dixella attica is only 9 and Dixella aestivalis is 32. So apparently we see that there is a difference between their frequencies. So now we want to confirm that whether this difference is a significant difference or this difference is not a significant difference. So for that purpose, we are going to use the chi-square test of homogeneity. So question is the distribution of frequencies between the categories homogeneous? So this is our question. And we are going to use the chi-square test of homogeneity. So what is the next step? The next step, after stating the problem and after choosing the type of the chi-square test that we are going to use, we have to state the alternate and null and alternate hypotheses. So our null hypothesis is the observed frequencies are homogeneous and the departure is merely due to the sampling error or scatter. So this is our null hypothesis, in which we are assuming that this difference is non-significant and this difference is only because of some sampling error or scatter. And then the alternate hypothesis is the observed frequencies depart from those expected of a homogeneous distribution by an amount that cannot be explained by sampling error alone. So in the alternate hypothesis, we're assuming that this difference is significant, and this difference is significant enough not to be accounted only by the sampling error. So these are our null hypothesis and the alternate hypothesis. So what is the next step after we have stated our null and alternate hypothesis? The next step is calculation of expected frequency on the basis of the null hypothesis that we have stated. So our null hypothesis was that the frequency distribution in all of these classes is homogeneous. So if our null hypothesis is true, we expect that 75 pupae should be distributed homogeneously between the 4 nominal categories. And for that purpose, we will do the calculation, which is how many categories or classes do we have? We have 4 classes. So 1 by 4 into 75, which is the total number of observations. So 75 divided by 4 is 18.75. So 18.75 number of pupae should be present in every category. And this is the table for the calculation of chi-square value and the chi-square value can be calculated by using this kind of a simple table. And in this table you can see that there are different columns. So the first column refers to the column in which we have stated our classes or our categories, and in this case these categories are the names of the species of these insects. So in the second column we have the observed frequencies that we have observed, and in the third column we have the expected frequencies, and as you can see that the total of the observed and expected frequencies, that should be same. And then in the next column we have the difference of observed and expected frequencies, which is O minus E. And then in the next column we have the square of this difference between observed and expected frequencies. And in the last column we have this square of the difference divided by the expected frequencies. So as you can see that we have to do this calculation separately for every class, and then we take the sum of the last column, and that sum is actually our chi-square value. So this is the method of calculating the chi-square value from your observed and expected frequencies. Now the calculations, the observed frequencies and the expected frequencies. Then we have the difference of observed and expected frequencies. So 24 minus 18.75, which is 5.25, 32 minus 18.75, which is 13.25, and then 10 minus 18.75 minus 8.75, 9 minus 18.75, which is minus 9.75. So you have to ignore this minus sign in the last two rows. Why? Because we are going to take square of these values in the next column, so it's not going to make any difference if there is a minus sign or if there is a plus sign with your values. So we are going to take the square of these individual values. So square of 5.25, which was the difference of observed and expected frequency of Dixella autumnalis. Then the square of 13.25, which was the difference between observed and expected frequency of Dixella aestivalis. And then the square of 8.75, which was the square of difference between the expected and observed frequencies of Dixella amphibia. And then the square of 9.75, which is the difference between observed and expected frequency of Dixella erica. And then we have our last column in which we divide this square of the difference between observed and expected frequencies by the expected frequency. So we have this 27.5625, and why I'm taking this long number is because when we round off during the initial stages of calculations or during these intermediate steps of calculations, we are going to end up with a different number and we are going to have a different result. So we have to take at least 4 digits after a decimal so that we have the precise calculation at the end. So 27.5625 divided by the expected frequency, and the result is 1.47. So we calculate that for every class. For Dixella aestivalis, the square of the difference divided by the expected frequencies is 9.3633. For Dixella amphibia it is 4.0833, and for Dixella erica it is 5.07. And now we have to take the sum of these values, 1.47 plus 9.3633 plus 4.0833 plus 5.07, and our sum is 19.987. So this is the value of our chi-square. This is our calculated value. Now our calculated value is 19.987. So what should be the next step? Next step is to see what is the degree of freedom, which is n minus 1. N is the number of classes, minus 1 is 3. So our next step is to see that what is the probability of a null hypothesis to be true, and for that purpose we have to compare our calculated value with the tabled value. And our null hypothesis is the observed frequencies are homogeneous and the departure is merely due to sampling error or scatter. So we are going to compare our calculated value with our table value to see that whether this null hypothesis is true. What is the probability of this null hypothesis to be true or no? So this is our chi-square distribution table, and in this table, as you can see, that we have the columns which represent the probability values for different levels of significance, and they are arranged in the rows according to the degree of freedom. So what was our degree of freedom in this case? It was 3. So what is our first level of significance? It is 0.05, and the value is 7.815. So what was our calculated value? Our calculated value was 19.987. So which one is greater, our calculated value or the table value? Obviously our calculated value is greater, 19.987. It means that we reject null hypothesis in favor of alternate hypothesis, and the significance level is 95%, which is said to be significant. Now we are also interested in seeing that what is our next significance level. That at this step we reject the null hypothesis. So null hypothesis stands rejected at this point. So in the further steps we are only going to see that what is our maximum significance level of these results. So what is our next level of critical probability or significance? It is 0.01, and what is the value there? It is 11.345. So this value is also less than the calculated value, therefore this result is also significant at 99% significance level. So this result is highly significant. And now we move on to our next level of critical probability of significance, which is 0.001, and here we can see that our calculated value is also greater than this value. This is 16.266, the table value at 0.001, significance level of 99.99%. So our results are very highly significant, that there is a 99.99% probability that our null hypothesis is false, right? So probability of a null hypothesis to be true is less than 0.001. Therefore we are rejecting a null hypothesis and we are accepting the alternate hypothesis. So what should be our results? This is our last step, the results. There is a statistically very highly significant departure from homogeneity between the four categories: chi-square 19.987 and probability less than 0.001. Distribution of the four species is not homogeneous in the population. So this is another way to state our results, that we say that the distribution of the four species of Dixella is not homogeneous in the population, in the community, and stating the chi-square value and the probability of significance of these results. So this is how we do the chi-square test of homogeneity, and this is how we state our results.